I was very close to concluding that there is something wrong with this question, because that's what we usually run to when we can't seem to answer a question. So let's take a look at 6.6 here. The question is saying the equilibrium constant Kc is 0.49 at 398 kelvins, and that is in graph B. Okay, and then the question itself: calculate the initial number of moles of P2Q. The initial number of moles of P2Q. So let's take a look at our situation and make sense of it. So consider the balanced equation for a hypothetical reaction that takes place in 2 decimeter cube sealed containers. So here's our reaction, okay? And then the graphs below, not drawn to scale, are obtained for the same reaction at 2 different temperatures. Same reaction, 2 different temperatures. Graph A is obtained at 298 kelvins, while graph B is obtained at 398 kelvins. So this is the information we have. Let me just jot down the Kc. The Kc is equals to 0.49. We're interested in the initial number of moles of P2Q. This is what we are looking for, and the information we have is these 2 graphs. So graph A is at 298 kelvins and graph B is at 398 kelvins. So we are supposed to use these 2 graphs in order to find the initial number of moles of P2Q. So one complaint I have with regards to this question is the hypothetical compounds that we have. We have PQ2 and P2Q. Is very confusing. Sometimes I'm using PQ2 in place of P2Q. I mean, if it is a hypothetical reaction, why not just use X and Y, A and B? That would make our lives very simple. Apart from that, in graph A, PQ2 is represented by a solid line, and then in graph B, PQ2 is represented by dotted lines. So to move from graph A to graph B, it becomes very painful. It becomes a very painful process. The compounds, they look the same, and then the graphs, in graph 1 we are using dotted lines. For the same compound we are using a solid line for in graph B. You know, I didn't really like that about the question, but you know, enough about me complaining. Let's see how we can solve this problem. So let's take a look at our reaction. P2Q is a gas, and then Q is a solid in the reaction side, so we can forget about this because it is a solid. We don't include solids when we calculate Kc. And then the product is PQ2. It is another gas, right? It's not an aqueous solution. So if we have gases, instead of using initial number of moles, changing the number of moles and number of moles at equilibrium, we can use the concentration if we have gases, right? So let me show you what I'm talking about. So we're going to draw our table. We have our 2 compounds, P2Q, and then we have PQ2. Okay, that is what we have. And then let me draw a table here and show you what I'm proposing. So let me make the spaces a bit bigger here, because yeah, we're gonna need some space. And then let's just underline here. Right, so let's see. This is the initial concentration. Okay, so the initial concentration, we're gonna get that from graph A at 298 kelvins. So P2Q, what is the concentration at equilibrium? P2Q, it is not given to us. Okay, so we can put X there, and then the concentration of PQ2 at 298, our initial temperature, it's 0.4 moles per decimeter cube. So here we have 0.4. Right, now let's come to the change and the final. Well, at 398 kelvins, that's where we have our final. Our the concentrations we're interested in are at this part where our reactions, well, our reaction is at equilibrium, right? Rate of forward is equal to the rate of reverse. The concentrations are not changing. Okay, so let's check P2Q. P2Q, we had X initially, and then now at equilibrium here at 398 degrees, 398 kelvins, I mean, we have 0.35. That is with regards to P2Q. Let's check PQ2. Well, with PQ2, we actually can read the value here because the value is here and the graph is not drawn to scale. So we actually don't have this. But we can solve for that. How? Well, we can find the change that happened to P2Q and then use it to find the change for PQ2, right? Using the balancing coefficient and find the final concentration of PQ2. So let's go ahead and do that. But we need to know whether from 298 to 398 is the concentration of P2Q increasing or is it the concentration of PQ2 that is increasing, right? Do you just hear that P2Q and PQ2, they sound the same? Now it's confusing because which one are we talking about? But let's take a look. Initially, the concentration of P2Q is less than 0.4, right? At equilibrium. And then after that, it is at 0.35. So we cannot actually tell whether this value is less than 0.35 or is greater than. Why am I saying we can't tell? We can't tell because the graphs are not drawn to scale. This can be 0.39, right? Because it's not drawn to scale, so we cannot decide anything. But let's check PQ2. Initially, 0.4. And then after that, it is clearly less than 0.35, right? Because we cannot have 0.5 here, below 0.35. So that we can conclude that PQ2 has decreased from 0.4 to less than that. So it means that here we're going to have plus and here we're going to have minus, right? At least we know that PQ2 is getting reduced from 0.4 to less than that, and then P2Q is getting increased. So we started with X and then X plus something, X plus something. This is the change we're looking for. Give us 0.35. So what must this something be? What must this something be? Well, that something, if we solve for it, we should have 0.35 minus X. So here we have plus 0.35 minus X. Okay, if we add these two, we have X minus X, which is 0, and then X, and then 0 plus 0.35, that will give us 0.35. So that is fine then. Now let's move to the other side. The balancing coefficient is 2 here, so we're going to have minus 2 multiplied by 0.35 minus X. Okay, now let's find the final. So we're going to have minus 2 multiplied by 0.35. So that will be minus 0.7. Well, don't want to make any mistakes. So 0.35 multiplied by 2. Hey, 0.35 multiplied by 2. 0.7. Okay, that is fine. So I have 0.4 minus 0.7, which is minus 0.3. So, and then X minus 2 multiplied by minus X. So we have 2X minus 0.3. Okay, this is the final that we have. Let me just double check and see if my final is correct. Okay, when I add these two, do they give me 0.35? X minus X. Okay, that is fine. Now let me check the other side. 0.4 and then minus 2 multiplied by 0.35. that will be minus 0.3. That is fine. And then minus 2x multiplied by minus x, that is 2x. So 2x minus 0.3. That's fine. So these are the concentrations we have at equilibrium. So we can then say Kc is equals to concentration of PQ2 squared divided by the concentration of P through Q. Okay, let's substitute. Kc is 0.49. PQ2, we have 2x minus 0.3, and we square that. Everything divided by P through Q. P through Q is 0.35. So we can cross multiply. 0.49 multiplied by 0.35. This is 0.14. And then this is equals to 2x minus 0.3 squared. If you factorize here, your life is going to be complicated. The best thing to do at this point, well, let me verify something. 0.49 multiplied by 0.35, 0.1715. This is 0.1715. So 0.49 multiplied by 0.3. Yeah, I had substituted the wrong thing initially, but that is fine. Okay, so if you go ahead and square there and expand, you're going to complicate your life. The best thing to do is to take square roots on both sides. So now I need to Google the square root of 0.1715, as I don't have a calculator with me. When I do that, I get 0.4141 is equals to 2x minus 0.3. We took square roots on both sides. So 0.4141 minus, well, plus when it goes to the other side. So 0.4141 plus 0.3. This is 0.7141 being equals to 2x. So let me divide that by 2. 0.3571 is equals to x. So there we go. That is x. This is the initial concentration of P2Q. Initial concentration of P2Q is 0.3571 moles per decimeter cube. But we're interested in the number of moles. We have calculated the concentration, the initial concentration, but we do have the volume. It is 2 decimeter cube. It's given to us in the question statement. So we're going to have 0.3571 multiplied by 2. Well, we're going back to 0.71. So 0.71 moles is the initial number of moles of PQ2. Let's talk about it. Which approach did you use? Are you finding any loopholes with my approach? Let me know in the comments.